All right, so, okay, so let's think about that. So this is the degree of abstraction we're sitting, is what I mean. We're sitting right at the boundary of like binary. So binary is just a mathematical space, right? You're thinking, oh, I'm gonna add two binary numbers together. I need an AND gate, NAND gate, AND gates, NAND gates, as drawn here. Okay, obviously, this thing does not exist. Okay, this is just a figment of our imagination. Okay, what exists, what starts existing, and this is the boundary here, is the transistor that actually exists. Okay, so just remember when you're doing your project. So Paul, this is like I'm coming from the what do you call it, from the sublime to the more question that you're asking for, is when you're doing your projects here, remember that what you're building are digital circuits. Okay, so when I say build an inverter, what does this inverter need to do? It needs to, you got to first go back and think about an inverter and how you think about an inverter. The next level up from this class, is, again, stop me if you guys are not familiar, is like sort of what you see in your function generator or your Verilog simulation or whatever. You've got zeros and ones, okay, and with some timing, whatever it is. Okay, you guys with me? So this is just one step above us from this class. So what we're learning in this class is how to make stuff that does this, the real this. Because again, zeros and ones don't exist. Two different voltages exist. We can call, so what we do is we call one of them a 0, and we call the other one a 1. And there's no perfect edges. Perfect edges don't exist. Perfectly fast edges don't exist. There's some rise time, fall time, and that's what we see in the circuit. So going back to when I say make an inverter, whoops, what the heck happened? Great. I don't even know what that is. What did I just do? All right. Okay, so when I say make an inverter, I mean, this is, so what I by that mean is this is the inverter that exists in our mind's eye, and it's got a transfer function like this. Okay? And I would like to build that with transistors. Okay. Now, notice a couple of things about inverters. Okay? The first thing is there's only zeros and ones. There's no, if I told you, simulate this, tell me what this inverter does with an input from this truth table. What does this inverter do with an input value of 0.9? What would it do with an input value of 0.5 from this truth table? That does not exist in this world. Okay? It does exist in this world if you screw up, right? So, I mean, it's a transition point. As I go from a 0 to 1, in the real world, I cross something that you say, well, if by 0.9 you mean 90% of a 1, whatever voltage I have for 1, I'll cross that point as this guy does its transition. At some point I'll cross this, but at no point, this is the 90% point. So say this is 0 volts and this is 1 volt. Okay, so I'm pretending this is binary 1 and this is binary 0, and I'm going to use this device to do my binary math because this is the only thing that the real world gives me. Okay, so at some point I will cross a point that's at 90%, but this is not something I'm dwelling on. Okay, it's not a legitimate end point or beginning point for or binary math. You're just sort of trying to get there, stabilize to a real 1 or a real 0, and then look at your output. Okay? So when, for example, when you're doing, so what will you look like? So Paul, going back to Paul, if you're doing, my favorite, what you can do is you make your NAND gate. Standing room only. No, I'm just kidding. Where's a good place? There's a place to sit. Okay. What would I do here? I'd do something like this. So if I had two voltage sources going to A and B, right? So if I had, A doing this and B doing this. Okay, so this is like just a stupid way of doing it. So you have them both start at the same time. You have B pulsing at twice the rate. Then you can end up with 1, 0, 1, 1, 0, 0, 0, 1. And then you look at what the output does, okay? But this is the legit places to, so what you would do is you would show me this as your input. You would show me this as your output, whatever the heck is gonna do, I can never remember. So it's a 0, whoops. It's kind of 0 everywhere except whether I want both 1. Sorry for my handwriting, guys. So it's going to do something like this, I think, as a truth table, minus this stuff. Okay, and then what you would do is you go, okay, hey, as you can see, if you're really gonna, you don't have to go this far, but if you look at these times, you see that I get this truth table with the 0s and 1s, and then okay, that's your showing to me that that's a NAND you made. And it works as a NAND, okay? Now, this thing might do some really funky stuff, okay? Because, again, we're talking about the real world. For example, right here, when edges are right on top of each other, you might see like a glitch, okay? It might do something and then kind of change its mind, the way you're... Part of the reason I like to do it kind of like this particular exercise, is we don't have too many points where both inputs are transitioning at the same time. Because when both inputs are transitioning at the same time, you can get some funkiness here, right? You don't know which one's coming first, which one's coming second. Because the devices are stacked on top of each other, they might both be on at the same time, off at the same time. One of them might go on or off at different times. You might get a glitch. So it's not unusual in an output, depending on what your waveform looks like, to see something. It wouldn't happen in this waveform, but just saying, right? You might get a glitch because you got some non-allowed or some input that's not allowed just because you're doing transient analysis, okay? Does that make sense? Okay. So how do you actually use these gates in real life, right? Usually we have, I guess in my experience, I'm not big digital design. You have synchronous systems, right? You're just not, things aren't willy-nilly happening at any point, right? So that you have inputs, if again, going back to my binary abstraction or digital abstraction. The inputs are coming in at particular times. There's a clock. We'll see how we deal with a clock in a little bit. There's a clock happening, and the transitions are happening more or less on some edge of this clock. Okay? So these inputs are going to our NAND gates, okay, when at these points happening, and then you look at this NAND gate when things have stabilized, because there is a possibility of some glitchy business happening in a combinational circuit. Okay, did I mention these are combinational circuits? Did I mention the concept of combinational circuits? No. Blank page? Okay, good. So, no, not good, sorry. So, there's two kinds of circuits generally for digital circuits. There's combinational circuits, and then there's sequential circuits, okay? So combinational circuits are these things like NAND gates, NOR gates, inverters, whatever. They're combinational because their output is only a function of a combination of what's at their input. They don't have any memory of what happened, that there's some unit of time before. Sequential circuits do understand sequences. So there are things like flip-flops, et cetera. So we'll talk about this just a little bit later, but it's kind of like the vending. I like to use the vending machine as an example. The vending machine, if it was only made of combinational circuits, when you fed it your money, let's say you were using coins, when you fed it the money and went to select your drink, it wouldn't realize that there was a time before where money was fed in. Does that kind of make sense? Whereas a sequential circuit realizes, oh, there's a sequence of events here. Money gets fed in. This puts me into this new mode of operation where I'm just waiting to have my button pressed. Okay, button pressed. Okay, I remember my button got pressed, so my robotic arms comes and grabs it. Combinational circuit wouldn't understand that. It's just looking at whatever's happening on its input and the output. To first, we'll see this is not the case in reality. There's delays and stuff, but very incremental, small delays, right, on the input. So we're talking about combinational circuits. So anyway, long story short, when you're doing your simulations, I get all sorts of weird, especially at the beginning of these projects, all sorts of weird projects coming back to me, like, instead of zeros and 1 volt, there's some like waveform that's like not quite settled or doing something funny here. It's like you want to show me that this acts as like a digital circuit. The legitimate zeros, legitimate ones, okay? And this first one, I'm saying you don't need to worry about actual delays, right? You can just wait there and let it settle. Don't worry about how you size these devices and stuff. You'll learn how to size stuff, okay? So that's a main thing. So again, first two things I wanted to talk to you guys about: this degree of abstraction, which is a very, very important concept for all in engineering. Certainly in chip design, it is very important, okay? Because you constantly have to jump up and down in that degree of abstraction. You rarely jump 5 levels up and 5 levels down, right? The guys designing that chip are also not programming the application for your cell phone, right? But the guys designing designing the digital circuit might go back to talk to the guys designing the circuits and have a strong discussion about why their digital thing is not going to work, because this process technology is too slow and you're trying to cram, the usual cramming 10 pounds of shit in a 5-pound bag. So back off, guys. I can't meet this in the right domain clock amount. You got to back off. Those kind of discussions. That's just moving between 2 degrees of abstraction, between the guys writing the Verilog and the guys designing the actual clock network with inverters and all that stuff and looking at actual waveforms. Okay, so that happens all the time. Okay. And the other place where it happens, your chip comes back, and guess what? Your chip doesn't work. It blew up. Okay, now you might want to jump down 3 degrees of abstraction and look at your device and go, ooh, I didn't do a good job of designing the electrostatic discharge circuitry on that output. It's blowing up as soon as somebody touches it. Now I got to go debug a MOS transistor. Okay, so that does happen. Sometimes in debug, things open up, but when you're doing design, you're usually cycling back and forth. Like, I'm just assuming if you're writing these applications, you might be jumping between that and the operating system, or, you guys get the idea about what I'm talking about, the degrees of abstraction. And I'm just assuming this is the only field I've ever worked on, is chip design. So I don't know for sure, but it seems to me like no engineering could possibly work if you did not have the same concept there, because these projects are just too big. If you're making I don't know, if you're working for Southern California Edison or something and you're delivering power to someplace, if every time you get to a fuse you're doing E&M calculations or something, worrying about Maxwell's equations, it's never gonna get there, right? At some point you think as a fuse is a fuse, I don't know if that's what they have, or a cable is a cable, So that's, you don't think about, well, let me do the electric field lines and stuff around there, you just go, okay. But then there's some dude down there somewhere that's like designed the cable, or maybe they're selecting the cable for the company, realizing that this thing's got to run 10 kilometers, and they're doing electromagnetic analysis. But when they give it to you as just a cable with a certain resistance, you guys, a certain weight, whatever, you guys get the message. There's degrees of abstraction, okay? The other place where we see the degree of abstraction is so anyway, that's, any other questions about the project? Paul, was that a short enough answer for you? Okay, sorry. And then, guys, I'm like not always great at responding, but I would try to, if you really if it turns into a cluster, send me your LT Spice deck. Hopefully I can look at it and, try to help. Yeah, okay. Okay, so here's another concept. I think I already talked about it, and so nothing on the projects, right? You guys are gold. Good. Everybody's happy. Just one more administrative thing. Did what I say about being late one time by a week being okay, and after that, like, don't be late, or don't be too late. And then the turn-in time from now on, I'm just gonna make it be Saturday at like 8 a.m. or what did it say, noon? Noon, Saturday at noon. It's a good time. Who's going to wake up? Who's going to be? English Premier League games are running at Saturday before noon in the morning. So, okay. So the other degree of abstraction, do I want to talk about degrees of abstraction? Yeah, let me talk a little bit more about, because there's these two parallel things in terms of degrees of abstraction. So this was overall engineering activity. And now let's talk about the degrees of abstraction in our circuitry when we think of CMOS logic, okay? So where your simulation is at almost the simplest degree of abstraction, where I said, look at these switches. Of course, you're running SPICE, right? So, because that's our tool that we have. But basically, we're at a degree of abstraction of looking at these things as switches that are either open or closed, depending on whether the gate is a 0 or a gate is a 1. Gate is a 1. Gate is whatever. Oops, gate is a 0, gate is a 1. Okay, you guys get it, right? So that's the simplest level of abstraction. The next level of abstraction is, I think I may have mentioned this, but that an NMOS, for example, is not good at passing a relatively high voltage. So remember that a 1, like a binary 1, is your highest supply voltage. So it could be, in our case, I think for this class, we're probably going to be sitting at 1 volt because we're in the, what the heck are we at, 45 nanometer or 40 nanometer node, okay? So it's of 1 volt, a binary 1, okay? So if you're asking a NMOSFET to pass a 1 from this point to that point, you're asking it to do too much. It's not gonna like doing that. It's not good at that. Okay? A MOSFET, an NMOSFET, NMOS is good at passing low values. So if you get if 0 is 0 volts, thankfully that's easy to remember. So like NMOS will pass 0 volts all day, okay, from source to drain, but it's not good at passing a 1. And we'll see why that's the case. And a PMOS is good at passing a 1, but not good at passing a 0. Okay, so this is the next degree of abstraction. Okay, so simple switch, then a switch that has like a problem with one of the, that's like better at passing a certain range of voltages than another. Okay, the next degree of abstraction is thinking of an MOSFET as being a switch with a resistance and some capacitances. Okay, so that way we can start thinking of it again. We're still in the land of the dumb, right? But we can think of it as having some timing, some RC rise fall times, right? We have to have resistors and capacitors, a simple model. And then finally, which you've all been waiting for, is think of it in MOSFET as an actual, honest to goodness, transistor with currents and voltages running through it. Okay? This is all the same device. All the same device. And we're going to need to do all these, look at all these different modalities. Okay? There's even another layer beyond this, which is the MOSFET with like leakage current, drain-induced barrier, like all the second order effects. Which aren't going to be so second order by the time you're in the 45 nanometer process node. Okay. So back in the day when this whole business started and they were looking at CMOS as a logic family, like in the 80s or whenever the heck it was happening, 0 was a 0, 1 was a 1. When I said like it was very popular because of low power consumption, because it wouldn't burn any power at either end. If it's not transitioning, it's not burning power, so that was what made it popular. Well, guess what now? You do burn power when you're not in transition. By the time you have got 20 billion transistors, each one just has a tiny bit of leakage. You multiply it by 20 times 10 to the 9th, 20 billion, and you end up with like amps of current, which is like a serious problem. And so we'll talk about that. Okay, so again, degrees of abstraction. So as your projects go on, I don't know exactly, my vision was, I don't know how this is gonna go, is to move you guys so you're comfortable with this. We move to this, maybe this, whatever. We'll move down to the degrees of abstraction, and then talk about combinational and sequential circuits. Okay, so just as where we left it, any questions, by the way, so far about the one downside of this method of teaching, which is you guys, me not using my slides and not lecturing, I also have lost all sense of discipline, so I'm just sort of worried that I'm meandering. But it's good for me because I'm trying to hit like what I feel are important concepts for you guys without letting the slides kind of like get too much into minutia, because the minutia is there if you guys want to, and I suggest you do, but so this is helping me tell you guys what the important things are and the big concepts, but also have a chance to meander. So stop me if I'm not making any sense. This is all good for you guys. Okay, so let's quick review of what we talked about last time. We said we have this. So again, sorry, take a step back. So we're in this. We're trying to implement this digital binary world. Okay, we're ideally, we just would have these perfect switches. We would have never heard the word MOSFET. We'd never heard the word voltage or current. For a bunch of computer engineers, no disrespect, maybe like not computer engineering people, but computer engineers. We're building zeros and ones, and we got these switches that we don't have that in the real world. Okay, so you're ideally in that state, but now we actually have to implement our zeros and ones in our programs and so on into some actual functionality, okay? And you do that through the intermediaries. I'm at this level of abstraction, guys. Sorry. I'm talking to you guys now up, let's say up here, okay? So let's stay out of here for a while. So what I try to do is basically I still have to use gates, right? I wish I could just write code, right? But at some point, let's say my world ends at gates, I have to implement gates, okay? So what are these gates? These are called logic families, right? At the moment, really there is no other logic family other than CMOS, honestly. I can't think of anything else, right? There used to be lots of, if you guys work in the space program or some military stuff where they're using old stuff because, everything has a 20-year lifetime. You might have heard of TTL or some other weird logic families that no longer exist. There was a while where they had different logic families that you could choose from, and they would have different characteristics, right? But now, essentially, you have one logic family. It's called CMOS, static logic family, okay? And so what would distinguish as a customer of a logic family, not as a designer of the logic family. So now you're the person who's the customer. You want to turn your zeros and ones into schematics. So think of yourself as the customer. You're trying to pick and choose which logic family. You have a few things. You're looking at benefits, right? You're not you're not worried at this point about how am I going to design this. You're looking at as a customer, well, what's the power consumption? What's this? What's that? Okay? So as you looking at the CMOS logic family, like I mentioned, the primary winning point for CMOS was power consumption, or reduced power, much lower power consumption. Okay, that was it, because it was turning into a real huge problem. And so what that meant is it led to this thing where you had a PMOS network on top. So this is your VDD. It's clear to you guys, VDD in this class means your highest supply in the process. In our projects, it's 1 volt, okay? And then ground, you have your NMOS network, and the input goes to both, and the output comes from where they meet, okay? So this people did because they could, primarily, because they could have a situation where at no point, except during transitions, at no point in a steady state is VDD connected to ground, okay? It's either this branch is on, so either this branch is on and this branch is off, so no current flows through, or this branch is off, this branch is on, so no current flows through from VDD to ground, except during transitions.
What does that say?
Oh, sorry.
Your arrow at the very right side.
Oh, out. It's the output. I'm sorry, guys, for my terrible handwriting. So, okay, so we said power consumption is the primary thing, okay? That was a benefit in CMOS. That's what made it win. Okay, so we won, but this logic family has other characteristics that are important to the customer, whoever's going to use it, okay? So let's talk about some of those other ones today, okay? So, I talk about 1 volt as being a supply voltage, right? Why not use 1 microvolt as a supply voltage. I'm going to use 1 microvolt as the power supply, because remember, power ultimately is current times voltage, right? So that's the instantaneous power consumption. Okay, so the power I'm drawing from this guy to charge and discharge this capacitor. Okay, everybody with me? So why don't I just make this, I'll make life easy for me, I'll make this 1 microvolt. So then I can have 1 mega amp of current in my chip, and I only burn a watt. My cell phone will run forever. So any ideas why I wouldn't use 1 microvolt?
Your wire,
Huh?
the wire,
The wire? What do you think about the wire?
to expand.
It's going to expand
Yeah.
at 1 microvolt. Why would you say that? Oh, you're talking about the massive amount of current.
Yeah.
Yeah, but I mean, you don't have to run a mega amp through it. You could drive a 1 milliamp. But my point being is why are we stuck at a volt or something? Why are we not stuck? Why don't we just keep going down? Go ahead. Can I get your names? Sorry.
Ethan,
Ethan, what was your name?
Push.
Gush.
possibly like noise coming in, like,
Yeah.
like if you have one microvolt, you could assume logic 0 or 1 because of noise.
Yeah, so noise is a huge issue, okay? So that's the thing I was gonna talk about today, is your noise margins, okay? This is the next step, okay? So I'm an analog designer, I have to like admit. So I only do digital design when I'm forced to. So I usually think in analog terms, okay? And so there's in my world, by the way, everything I tell you guys is just my opinion, okay? I have, I don't deal with like truths and things like that. It's just my humble opinion. But I do have some, I've designed a few things that worked, some experience. So when I say stuff like, oh, this is only this and also only that, just remember that this is how I see the world. And I have like, I'm like simple-minded, so I believe in simple models of the world, right? Okay, so this is sort of caveat about this. So there's 2 kinds of noise, the way I see it in the world. Electronic noise. Okay, so there are what I call analog noise, okay? Then there is system noise. It's still analog, but I kind of think of it as a digital noise. Okay, so what do I mean by that? So noise. The noise, we're gonna bring the noise back into if you guys remember, we have 4 parameters. We have cost, we have power, we have sort of specs or performance, and then we have reliability. Reliability means how much noise rejection you have. Part of it means that, okay? By the way, there's a third noise, sorry. 3 noise. It's like that. Have you guys Monty Python fans? Do you guys even know what Monty Python is? No. No Monty Python? I mean, they had the Spanish Inquisition, so there's always like one more thing. This is what happens with being old. Okay, so analog noise. What is analog noise? Is the way I call it analog noise. Analog noise is what you see when you sort of turn on your oscillator and you're looking at some voltage. Okay, so if you look at your oscillator, there'll be some time. You have your voltage, and you don't see 1 volt. What you see is, you see this. So let's say nothing else is going on, right? You just turned on your power supply. Okay, nothing else is switching. Nobody's cell phone is on. No clocks are going on in your systems. You just have this. Okay, just sort of this noise. So by the way, the reason I call it noise, as you guys I'm sure you know, it just comes from audio. It's when there's no music, you could still hear the sort of this noise, but it's really this unwanted signal on top of your wanted signal. That's the definition of noise. Okay, so this type of noise is things like I don't know if you guys are familiar with that. It doesn't matter if you're in or not. Like thermal noise. So this is like fundamental. It comes from the Brownian motion of electrons in a resistor. If you have electrons in a resistor, they tend to go back and forth, back and forth, back and forth, even if I don't have any voltage across it. So at any point, if I zoom in enough into the voltages, there's this variation in the voltage because as these things are jumping back and forth, back and forth. And its thermal noise is very broadband, meaning if you look at so the way to look at noise in analog, you guys don't need to, just for amusement, so just don't stress about this. You look at it either in the time domain or frequency domain. Jump between those. So in the frequency domain, white noise is broad. It goes from 1 hertz as far out as you want to go, gigahertz, terahertz, whatever, out. Okay, so you got things like thermal noise. The reason I mentioned Brownian noise is because I want to drive the point. I don't know who Brown was, but sounds like an old dude, sounds like a fundamental type of noise, electrons moving around, resistor, pretty fundamental, right? Okay. Then you have flicker noise. So this is more like a 1/f noise. So if you look at the frequency response of this noise, again, you don't have to remember any of this stuff, just remember the analog noise. Okay? Is if you look at this response, it has like, it's worse at lower frequencies, lower at higher frequencies. But basically, if nothing else is happening in the system, you just have a resistor, you're looking at, across it, you'll have this noise. Okay? So that's your analog noise. So this by itself already sets some lower limit to your noise. So just think of the thermal noise, okay? Are you familiar with, are you guys have done probability distribution functions, probability theory, Gaussian probability distribution? Okay, so if I draw the, sort of, this is, white noise is Gaussian, so it's a little easier to do. So if I look at if I draw the amplitude distribution of this thing over here, you'll see something like this, right? So you'll have, this is distribution. Okay? So a lot of the times the noise is around here, the value, not the noise, sorry, the value of the signal is here, less chance of it being here. Notice I don't have any drawings here, so there's very little chance of any signal here, yeah.
You can't see your cursor.
You can't or you can?
No.
Oh, sorry. Thank you. So, there's a very good chance that you're seeing, like a Gaussian distribution. I forgot, like, I can't never keep this together, but if you're like 3 sigma away from the center, that's like 97% of the time you're there, right? But there's still a finite chance that every once in a while you'll have some data here. It's a Gaussian distribution. It's like going, you might have like 1,000,000 volts if you sit there and wait for it long enough. Okay? So, okay, what does that mean? That means if you had, like Ethan said, Thank you, Ethan. So if this was 0 and this was a microvolt, okay, this would be like half a microvolt. Well, who am I kidding? If this was the way it looked, it wouldn't look like this. It would look like this. Right, and this was your threshold. So you're like just sitting there, your NAND gate with the power supply at 1 microvolt is just, random number. It wouldn't even make sense, sensible stuff, right? And you can make it 1 millivolt and 2 millivolts and 10 millivolts and whatever. So pretty soon you start going above the noise floor, but you still have a bit error rate that you want in these circuits, okay, in digital circuits. So what do I mean by that? So in the last section, I was talking about how analog computation, to some extent, for some functionals, is a viable option, right? If you have an op-amp or an amplifier or something like that, Remember the flags analogy, but you have 128 flags versus 14 flags, 14 flags. So the 128 flag analogy was I would have a 7-bit analog system, and I would have, so I'd have go from 0 to, let's say it was 1 volt here, and have these really small steps that would represent each sort of number. And I can add 2 of these analog-ish numbers that have all these steps in between. Do you guys follow me? So here, one problem with this obviously is the noise, right? Because these steps tend to be small. If I have the same power supply of 1 volt power supply for a binary function, I have 1 step, 0 or 1, right? Here I have 128 steps between 0 and 1, so I'm not good at doing math here, but we're talking about maybe 10 millivolts or something in these steps. So you could have, this is like much more susceptible to noise, right? You could easily end up, you're trying to add 2 7-bit numbers. Maybe it'll work. Yeah, it might work. But what if you're trying to add 2 12-bit numbers? All of a sudden, each one of these steps off of 1 volt might be like 250 microvolts. Okay, so now you got an issue. But it does have one advantage. If I have noise here and I make a mistake, okay, I will mistake say a 10, a number 10 for a number 12. Okay, or maybe I'll mistake it for an 8. I'm not going to make a mistake of 10 for 100. Okay, now imagine if you had a binary system. Okay, and for some reason I decided to use a 1 millivolt power supply for this thing, and I had a mistake in my numbers, right? Who's to say that that mistake won't happen in my MSB, right? I mean, it might happen in my LSB, but it might happen in my MSB, right? So you could have a catastrophic error when you're in a binary environment with mistakes. Okay, so there's this concept of bit error rate when you're doing digital communication. Bit error rate is a number like 10 to the minus 9, 10 to the minus 12. It says how many errors are allowed if you have, say, 10 to the minus 9 bit error rate, BERT. If you guys go into communication, you'll be sick of this stuff. It says if you transmit a system that allows you to have a 10 to the minus 9 bit error rate, says you're allowed in 1 billion bits transmitted to get 1 error. Okay? Or in 10 to the 12 bits transmitted, whatever the heck that is, terabits or something, right? Small numbers, small errors are allowed. On top of that, most of these serial communication systems have error correction codes built in. Okay, so that's what allows them to even live